Hi, everyone. This is Dr. Beebe, and I wanted to go through some of the highlights of Chapter 7 with you. Now, Chapter 7 has a lot of calculations in it. Now, I'm not expecting you to do most of these calculations, but I do want you to understand kind of why these are important in the field of epidemiology. Okay, so we're going to be looking at hypotheses testing. So we've been talking about all these different study types these last 2 weeks. And now we're looking at how are we going to test the various hypotheses and what kind of relationship or association are we going to see and how are we going to measure that relationship? Okay. So the first thing we're going to talk about is statistical inference. And the whole idea of statistical inferences is it's being able to draw a conclusion about our entire population or our target population based on the sample. Okay, so when we are doing a study on a target population, whether it's female college students age 18 to 21, okay, um, if that's our target population for our research, we can't possibly survey or collect information from every female college student between the ages of 18 and 21. Okay. So what we do is we draw from that target population a sample, and we are hoping that that sample is a representation of our target population. Okay. So we use probability to indicate how reliable this conclusion is. So how reliable is it that the conclusion is that our sample is indicative of our target population. Okay. And obviously, as we've talked about in previous chapters, chance, bias, confounding variables all can influence or impact that association. So hypothesis formulation is just as it sounds. Okay. It's it's our guess. It's our best educated guess as to an explanation for what we're observing. Okay, because that's what hypothesis is. It's our best guess, our educated guess as to why what we're observing is actually happening. Okay, so our sample. So if the target population in which our health issue exists is small, um, we can have a better likelihood of determining whether the hypothesis is true or not. Okay. But remember, like I said earlier, it's rarely feasible for us to evaluate everyone in the target population. So we have to get this sample top population. And this is accessible, meaning we have access to this population. And we're hoping that they are going to ideally represent that target population. Okay. And to do that, we will measure the association from our sample or from our sample data to estimate the truth of our hypotheses. Okay. Obviously, some reasons for collecting samples versus collecting the entire target population. Obviously, it can be studied more quickly. It's much less expensive than trying to study the entire large population, which may even be impossible to do. Okay. Sample results can sometimes be more accurate than results based on populations because for samples, obviously, we're going to need more time, more resources that we need to spend on training the people who observe and collect the data. Okay. And all of these procedures that improve accuracy in our results. So testing the hypotheses. So hypotheses testing begins with a statement about which is commonly believed, about what is commonly believed, and that's considered the status quo or the null hypotheses. We then make a statement that contradicts the null hypothesis called the alternative or research hypotheses, or H1. So step one of evaluating the hypotheses, we're going to formulate the null hypotheses in statistical terms. Okay, so the null hypothesis is typically set at no association. So if we're studying something such as the presence of snacks and drink machines in the schools with childhood obesity, we would say that our null hypothesis is that there's no association between the obesity in the students and the presence of these snack and soda machines. So that would be the null hypotheses. And then we formulate the alternative hypotheses in statistical terms. So what are we wishing to test? What are we looking for an association between? We assume that the null hypothesis is correct unless there is sufficient evidence from the sample data to indicate otherwise. So the research hypothesis is our tentative suggestion that a certain phenomenon exists. So if we think that the presence of these snack and soda machines is influencing or has an impact on the obesity data that we're getting from the student population, then that could be our research or alternative hypotheses, that there's an association that exists between those two variables. So we might think that there's a positive association, meaning the presence of the soda and snack machines is leading to an increase in the childhood obesity data. In step three, we're going to select the level of significance for the statistical test and the sample size. So the level of significance is generally 0.5. But if we're looking at a more conservative test, we might use 0.01. In exploratory studies where we are kind of throwing more feelers out, it may be as high as 0.1 or higher. Okay. Of course, then selecting an appropriate sample size is necessary to ensure that sufficient power exists to evaluate the hypotheses. Step four, we're going to select the appropriate test statistic and identify the degree of freedom and the critical value. The degrees of freedom is the number of independent pieces of information used to obtain an estimate. So it's basically the number of independent observations in a sample minus the number of parameters estimated from the sample. So the critical value is a value on the distribution of the test statistic under the null hypotheses that identifies the values for which it rejects the null hypotheses. And then step five, we're going to collect the data. We're going to estimate the measure of association and calculate the appropriate test statistics. If the absolute value of the test statistics exceeds the critical value, then we're going to reject the null hypotheses in favor of the alternative hypotheses. Otherwise, we do not reject the null hypotheses. So some test statistics that we're going to talk briefly about. And once again, I'm not going to ask you to calculate any of these. I just wanted to kind of introduce these ideas to you. If you take a higher level epidemiology class later or a higher level statistics class later or biostats, you will talk specifically about these tests. Okay. The p-value. So the p-value is important. The p-value tells us what is the likelihood that what the results that we're seeing are due to chance. Okay, so if they're due to chance, then it's not a direct measure of our association. Instead, it's due to chance. So a p-value, the level of significance is 0.05. Okay, so when the test statistics are computed using software, you're going to see that p-value alongside the test statistic. Okay. Confidence intervals are ranges of reasonable values in which a population parameter lies based on a random sample from the population. So as the sample size goes up, the role of chance goes down. Okay. And this is reflected by the confidence interval, which becomes narrower. Once again, I'm not going to ask you to calculate any of these values. However, it is important not to memorize these, but to look at the different study designs that we have. And we've talked about these study designs: ecological, cross-sectional, case control, cohort experimental, just to look and see what type of statistical test or measures of association would be appropriate for those study designs. Once again, not going to ask you to do any of these. I'm not going to ask you to spit back any of these formulas. Okay. We talked a little bit about the different types of data in the last semester, or I'm sorry, in the last chapter. With nominal data, we look at the contingency table, and basically it's uh, a type of table that shows the frequency distribution of two nominal variables. Okay. The most common one used in epidemiology is the 2x2 contingency table to evaluate the association between a two-level exposure variable and a two-level outcome variable. So our outcome variable is yes or no, meaning case or no case, and our exposure variable or risk variable is yes or no, exposed or not exposed. So that's our 2x2 table. Okay. And once again, not going to ask you to calculate this, but this does show nicely how these numbers are calculated and these outcomes. Cohort risk data. Once again, just showing this to you. Please do not take time to learn this or to practice this. Okay. However, it is important for you to understand that the risk ratio ranges from 0 to infinity. If the risk ratio comes out to 1, that means there's no association between exposure and outcome variables. If it's greater than 1, it's a positive association, meaning as one goes up, the other goes up again, versus risk ratio that's less than 1, and it's a negative association. So they are going to be going in opposite directions. Okay. Once again, do not memorize these at all. Okay. This goes through an example. I'm not going to ask you to do this, but sometimes it is interesting to kind of walk through the examples on your own. Same with the rate ratio. Attributable fractions. This indicates the percentage of cases in the population attributed to the exposure. All right. So it's going to tell us what are the number of cases that are exposed and the percentage of cases attributed to that exposure. Okay. And once again, I'm not going to ask you how to do any of these, but I think it's important for you to understand that with these different study designs, we have different measurements of association. Odds ratio is something that we did talk a little bit about in the last chapter too. This also ranges from 0 to infinity. It's going to go very similar to the rate ratio we just talked about. If the odds ratio is equals to 1, that means there's no association between the exposure and the outcome variables. However, if it's greater than 1, the same as we saw before, we're looking at a positive association. Okay, so the odds of exposure among cases is greater than the odds of exposure among non-cases versus a negative association in which the odds of exposure among cases is less than the odds of exposure among non-cases. Okay, this tells you how to calculate confidence interval. Once again, never going to ask you to explain this or to calculate this. But if you'd like to, you can work your way through this example of the odds ratio. Okay. When we talk about the effect modifier, we're talking about when the association or relationship between exposure and outcome is modified by the level of a third variable beyond random variation. Okay. So once again, we skipped a lot of the information in this chapter because we are not requiring you to do any of these calculations. However, I do think it's important to still have this chapter and to understand that with these different study designs, we do have different measures of association. And the whole idea is to tell us kind of what is the relationship, what type of relationship, if any, exist between our exposure and the health outcome or health issue. If you have any questions, please let me know. And we are getting very close to the end. So hang in there. You all are doing a wonderful job. All right. Take care. Thank you. Bye-bye.